climate smart watershed. We gave wide publicity through our website as well as through the WhatsApp groups, and we received 630 applications, of which 132 participants have been shortlisted for this particular training. They include 83 students, 44 faculty, and 5 from different industries. So the total is 132, and we have got 32.57% of lady candidates for this particular training. In all, more than 10,000 participants have participated in different 33 trainings or events, webinars, which have been organized by CAST CSAWM, in which we had some students, then some trainings were only for farmers, then some trainings were for students as well as faculty. And this particular training has got 3 different, as I have already told you, that students, then faculty, as well as some persons from different industry. Today is the first day of Ashad. So in second shlok of Meghaduta, it is said, Ashadasya prathama divse Megha mashlishta sanu vapra krida parinita gaja prekshaniyam dadarsha. आषाढ़ के प्रथम दिन एक बड़ा सा काला मेघ रामगिरी के शिखरों से टकराया। उसे देखकर ऐसे लगा जैसे कि कोई हाथी अपनी मस्ती में खेल रहा हो। So it is expected that we will have rains which would be with high intensity, and definitely with such rainfall we need the soil and water conservation interventions for saving our soil and for conserving the water. With these words, I would now request Dr. Barai to introduce our first speaker of today. We have got total 10 experts in this training from different background, some from bank, some from NGOs, and some from academic background. So I'll hand over to Dr. Barai.
Okay, thank you, Dr. Atri sir. Good morning to everybody. I welcome all the participants for this one-week training course on soil and water conservation interventions for climate smart watershed. Now I got the opportunity to introduce a dynamic faculty member from our university, Dr. M.G. Shinde sir, Professor of SWC, MPKV Rauri. He did his bachelor's degree at MPKV Rauri, master's from IIT Kharagpur, and doctorate from Loughborough University, UK, and MCM from Pune University, Maharashtra. At his credit, near about 50 scientific publications, 3 book chapters, 15 extension articles, 3 books published, and 19 different technologies released. He is a recipient of Commonwealth Academic Staff Scholarship Award and International Student Award for the year 2004 by British Council, London. He visited the 7 different countries for academic purpose. At present, Dr. Shinde sir is working as a co-principal investigator, CAST project MPKV Rauri. He is a co-convener of this one-week training program. He is engaged in the field of teaching, research, and extension from last 34 years in Mahatma Phule Krishi Vidyapith, Rauri, Maharashtra. Now, I request Dr. Shinde sir, opening batsman of our one-week training program, to deliver his speech on rainwater harvesting for climate smart watershed. Thank you. Dr. Shinde sir, please.
Thank you, Dr. Barai. So welcome all participants for this online training course on soil water conservation interventions for climate smart agriculture. Vaibhav,
Yes, sir.
I need to share the screen.
Yes, sir. Yes, sir. Visible, sir.
Visible?
Yes, sir. Yes.
Okay. So welcome again. This is the first lecture in the series of lectures in this online training program. So my lecture is on rainwater harvesting for climate smart agriculture. So as all of you know, the soil and water, they are the two primary natural resources which are under threat because of the continuous development processes, increased population. And they are very vital to the very existence of the human civilization, actually. So when we look at these the problems, especially the water problems in the rural areas, especially in the rural areas, so there is a lack of fresh and safe water supply for drinking, lack of water for agriculture and livestock, lowering of groundwater table. Water has to be brought from long distances, and mainly this task has to be carried out by ladies and children. Then often there is a poor quality water for human use and also for agriculture. Then if there is no water, of course, then it results into migration actually. So, migration to the cities and to the area where there is availability of the water. And if you take the context of the Maharashtra state, we often see that every year the government has to spend millions of rupees on supply of water through tankers. So these are the common problems which we face in day-to-day life about the water scarcity. Now, if again we take the in the context of the state of Maharashtra, this is the usual practice. 148 of the 355 talukas or tahsils in Maharashtra, they are consistently drought prone. And 84% area, cultivated area is dependent on the rainfall for its agriculture. So what is the solution actually? So there are two solutions. One is construction of the big reservoirs and the another is the rainwater harvesting. So construction of big reservoirs, it has to take place at certain topographical locations. It is not necessary that we will find those locations or sites everywhere in the state. So in Maharashtra, most of these sites, they have been exploited. And even the remaining sites which may not be economically viable, even if those are exploited or the dams are constructed there, still the area under these big reservoirs, it will not go beyond 30%. So 60 to 70% area in the state of Maharashtra will depend on rainwater harvesting for making the water available. As far as the India is concerned, this area will be around 50%. So 50% area in India will depend solely on the rainwater harvesting for agriculture or domestic purpose. So that signifies the importance of the rainwater harvesting. So it is the harvesting of the rain and resulting runoff where it occurs. That's what we call rainwater harvesting. Now, looking to the potential of rainwater harvesting, this is a theoretical statement, but still it has its own importance. Say, for example, if half of India's average annual rainfall of 1170 millimeter is captured over 1.12 hectare in each of the countries, 5,87,226 villages, then the 6.57 million liters of rainwater which is collected will meet the annual cooking and drinking needs for an average village of 1,200 people. So that is the potential of rainwater harvesting. Now, the water storage capacity, that is one of the important indicator about the development of these resources. Hello. So India's per capita water storage capacity is 207 cubic meters, whereas in Western countries, it is to the tune of 5,000 cubic meters. Now, these are additional supports for to denote the potential of rainwater harvesting. So, for example, 1 centimeter of rain from 1 hectare area, it gives 1 lakh liters of water. 25% of 600 millimeter rain will give 15 lakh liters, and which is enough to fill 30 by 30 by 4.5 meter size farm pond, which is again enough to meet water requirement of pomegranate on 1 acre area for about 8 to 9 months, of course, with micro irrigation. Now, rainwater harvesting is considered as a good adaptation measure for climate change. Climate change is believed to have a large impact on water resources systems, both globally and regionally. It has become a major global issue, especially in developing countries, because they are most affected by its impact. Rainwater harvesting techniques offer an alternative source of water and represent specific adaptive strategies to cope with water scarcity within future climate change. So this rainwater harvesting, these are the local measures or local interventions. Even if they fail, there is less risk of damage. They are decentralized and they are quite supportive to the local communities. Just a minute. Of course, they also come with some drawbacks, which I will discuss during the presentation. Now, basically, there are two major approaches of rainwater harvesting. One is in situ rainwater harvesting, which is capturing the rain where it falls, and another is the ex situ rainwater harvesting. So, in situ rainwater harvesting, these practices, they will be delivered by some other speaker. There is a separate lecture on this. So, I will not discuss about this in situ rainwater harvesting. Ex situ rainwater harvesting for some distances and storing at some distance with big reservoirs. So, for example, these Nala bunds, again, these are very popular structures in watershed development programs. They are constructed on the main streams in the Nala, maybe of second or third order. They recharge the surrounding area and the aquifer below. They hold the silt flowing through the streams, and it has got a good storage excavation ratio. Then the bigger structures in the watershed, they are percolation tank. They recharge large areas. Thousands of such tanks recharge the water table aquifer in Maharashtra. They're very good storage excavation ratio. Then these are the farm ponds. These are normally off the stream, where there is no stream, but there are undulating topographies or sloping topographies. We can have these farm ponds at the end of the slope. These may be again excavated farm ponds. They are also called as excavated farm ponds. So they serve as storage pond for domestic use and irrigation. They suffer from excessive evaporation and seepage losses, and they have poor storage excavation ratio. Now, when we come to the watershed development, then we have to integrate these in situ and ex situ practices. So this is a sort of definition sketch of integration of in situ and ex situ rainwater harvesting practices. So all these in situ practices like contour trenching, contour stone walls, contour bunds, they are integrated with the bigger structures like check dams, irrigation tanks. All these practices, they are integrated in the within the boundaries of the watershed. Now, in Maharashtra and out of Maharashtra, in India, huge work on watershed development has been done since the past, and still it is progressing. And there are many successful case studies actually. So I will briefly discuss a couple of case studies in Maharashtra. So this is the Darewadi watershed, which is developed by NGO Water, that is Watershed Organization Trust. It is in Sangamner Tehsil of Ahmednagar district. The area of the Darewadi watershed is 1,525 hectares. 2/3 is the private land, 1/3 is the forest land. 131 households are there. and main livelihood is sheep and goat farmers. Then the watershed has been developed with 87 lakh investment. The average rainfall is 400 millimeter, and it is completely water scarce village. These are the interventions in the watershed development. So there are farm burns, contour burns, horticulture, grassland with trees, afforestation, then drainage light treatments, nala burn. There are 7 nala burns. There are 48 gabion structures and 2 check dams. So see, after the watershed development, see how there is change in the groundwater level. So the vertical bars, they represent the rainfall from 1995 to 2000. And the greenish blue line, it represents the change in the aquifer levels. So you can see that the aquifer level is continuously rising because of the watershed development activities. And in 1998, there is a huge rainfall, 800 millimeter in the watershed. And but correspondingly, there is no sharp increase in the groundwater level, because during such events, if there is heavy rainfall, many times this rainfall is results into the runoff, and proportionately there is less contribution to the groundwater. So it has not resulted into the sharp increase in the groundwater table. So this is one successful case study of the watershed in Maharashtra. And you can see the statistics before watershed development, after watershed development, and January 2005 situation. So before watershed development in 1996, every year. But after watershed development, during the year 2001, the village is completely tanker free. And still it is tanker free. The average depth of water table below ground level was 6.5 meter below watershed development. And after watershed development, since 2001, the groundwater level is 3.5 meter below the ground surface. And as on today, it is around 3 to 3.5 meter below the ground surface. Then before watershed development, number of active wells were 23. Now they have risen to 67. Electric motors for pumping water, previously there were 6, now it is almost 65. And land under irrigation before watershed development was 197 hectare, now it is 381 hectare. This is what we call as a good intervention, good success story of watershed development, conducted by one very popular and promising NGO, Water in Maharashtra. There is another case study which is again quite popular, that is Hivre Bazar watershed. And this watershed development project is led by the Popatrao Pawar, who received Padma Shri award during this last year. So this village also very water scarce village. The annual rainfall is 350 to 400 millimeter. The total cropping is rain-fed. There is heavy soil erosion. There is a problem of water, drinking water, unavailability of water, unavailability of fuel wood. And this under the leadership of Popatrao Pawar, watershed development activities were carried out. And as a result of the watershed development activities, there is a rise in water table from 70 to 80 feet to 20 feet, 25 feet below the ground surface. And there is change in cropping pattern from the traditional jawar and bajra to more cash crops like onion, potato, and horticulture. And there is increase in the cropping intensity. There is increase in fodder availability from 1,500 metric tons to 6,000 metric tons, and increase in milk production from 300 liters to 3,000 liters per day. So these are the before and after photographs of the Hivre Bazar watershed. Now, what are the benefits of this watershed development activities or the projects? So there is decrease in the surface runoff, that is flash floods and soil erosion, increased surface water storage, increased groundwater storage, increased soil moisture storage, better crop yields, conservation of natural resources, better socio-economy of the village, better sense of cooperation and community ownership among the villages. Now, we have one of the biggest programs of watershed development in the country. There is an expenditure of around 2,000 crores per year. and it spreads from Rajasthan to Assam and Himachal Pradesh to Kerala. Now, the couple of case studies, success studies, which I just narrated, they are very few actually, as compared to the total watershed development projects in the state and the country. We don't find such success stories spread across different states of the country. The results, they are not encouraging at many other watersheds. Many watersheds projects have basic design flaws. During early period of watershed development project, there was a lack of community participation. Then traditional structures, they are not accounted in the development of the watershed. Failure in primary objective of land degradation, uh, often it is a failure of this primary objective. Then there is a lack of consistent criteria for selecting villages, lack of consistency in the norms of process of implementation of the watershed. So these are some of the hurdles which are being, removed or modified during the over a period of years. Now, again, it is a huge task at the current level of outlay. It would take around 75 years for watershed treatment to be completed in the country. And for the work to be completed by the year 2020, the government needs to allocate around 10,000 crores per annum. Now, important missing issues in the Indian watershed development programs. Now, these are actually very important because many times these watershed development projects, they are conducted in the remote part of the state or the country, where data collection and storage of data is often missing. Then evaluation of the project performance is also missing. There is no concern about the upstream, downstream development projects. Then there are issues of the equity, then sustainability of the projects. Many times the watershed development projects, they look like successful for a few years, but when the support of the NGO is taken away, then again there are the problems of the sustainability issues. And there is, of course, very little research support to these watershed development projects. So these are again some gaps. Say, for example, potential impact of water harvesting have undergone high degree of development. Then optimal level of water harvesting in different river basins that avoids unintended downstream impacts and ecological and environmental impacts of water harvesting in terms of reduction in environmental flows or increasing lean season flows in different hydroecologies. So such kind of studies we don't find in watershed development projects. Now, these are the challenges which are posed by climate change on rainwater harvesting. For example, in Asia especially, the freshwater availability is expected to decrease by 2050, affecting over 1 billion people. There are changing patterns in the rainfall amounts, the rainfall events may become more intense, increased frequency of flash floods and droughts. These are the predictions of the climate change and which the watershed development activities need to consider. Now, these are success stories which I narrated. I could just narrate you with the help of some parameters like rising groundwater table, then a change in the cropping pattern, change in the income level, change in the, say, for example, milk production, like this. But we don't have analytical kind of studies of these watersheds actually. Now, for example, suppose if you take any watershed, how the watershed would have behaved if there was different rainfall during the particular year, or how the watershed would have behaved there was different soil type, or if instead of 5 check dams there were only 3 check dams. So something like this. So we need such kind of answers to these questions, which at present many times we don't have, because there is a lack of data, there are lack of analytical tools or modeling tools. So to have such kind of studies or analysis, we need to go for modeling studies. And when you decide to go for modeling studies, then there are some prerequisites in the form of data. So for example, climate data, socioeconomic survey, and any special problems of the watershed. Then you have to go for peak rate of runoff, estimation of soil losses, upstream, downstream scenarios, then designing different practices, estimation of crop water requirements, and any special problems. So I will just share you one or two modeling studies which have been conducted as a part of MTech and PhD research. This is a decision support system for optimization of farm pond. This is based on the study of one MTech student guided by Dr. S.D. Gorantiwar, Head Agriculture Engineering Department. The objective of this study was to develop the model for estimation of water availability in the farm pond, then to develop the model for estimating the demand of water from different crops grown in command area of farm pond, then to develop the simulation model for estimating the crop yield and net benefits from the farm pond, to develop the decision support system for deciding the optimum size of farm pond, and to test the validity of the developed decision support system for a case study. So this is the conceptual figure of the farm pond, farm pond water balance and soil water balance. So when we say pond, then the input is rainfall and runoff, and the outputs are evaporation, outflow from other purposes, inflow from other sources. These are the inflow. Outflow for other purposes, for example, domestic. Then the outflows are seepage, evaporation, runoff, irrigation water delivered to the field, and then it goes to the soil water balance. Again, where rainfall is the inflow, evapotranspiration is the outflow, capillary rise is the inflow, and deep percolation is the outflow. And then the soil water balance gives the crop yield and the net benefits. So this is the equation of the pond water balance. So these are again a water balance equation which takes into account all the inflows and the outflows. So for example, the VT is the volume of water stored in the farm pond on Tth day. VT minus 1 is the volume of water stored in the farm pond on T minus 1th day. QT is the inflow in the farm pond through runoff on Tth day. QT1 is the inflow to the farm pond through other sources on Tth day. RFIT is the inflow due to rainfall over the pond surface area on Tth day. IT is the water released from irrigation on Tth day. SLT is the seepage losses from farm pond on Tth day. And ACT is the water loss due to evaporation from open surface on Tth day. WT is the withdrawal of water from farm pond for other purposes on Tth day. And V0 is the volume of water stored in the farm pond at the beginning of the pond water balance. That is when T is equal to 1. And the above equation gives the water balance of the farm pond. Then the pond can be of different shapes. So these are common shapes, rectangular. Then another is trapezoidal, and another is the circular. So these three shapes, they have been considered in this simulation model. So this rectangular shape, the volume of pond is given by this equation. Top surface area is given. Surface of wetted area of the pond is given. These are the straight geometrical equations. Then after change in the depth of the water, again, we can find the volume of the water in the pond, top surface area of pond, and surface of the wetted area. So all these equations, they need in the model to find out these different volumes and the different areas. Then trapezoidal or truncated pyramid pond. Again, we have geometric equations for different surface area, then wetted area, then volume of water after change in the depth of water, top surface area after change in the depth of water, and surface wetted area. This is a circular or cylindrical pond. Again, we have geometrical equations to find out the volumes and areas of this pond. So before the change of the depth in the water and after change in the depth of water. So these equations, they are fed in the water balance of the farm pond. Then the design of pond or deciding the size of the pond depends on the following parameters. So supply side and the demand side. So from supply side, runoff as a result of rainfall over the catchment area, then direct rainfall over pond surface, and external inflow from other source. Actually, when we say pond, normally we assume it is hydrological pond. So in a hydrological pond, always there is inflow from the runoff only, and there is precipitation over the pond surface. So there are only these two inflows actually, and this water has to be used for the domestic or the agriculture purpose during the dry spells. And there is inlet and outlet to the pond for the inflow water to come in and for the outflow to go out. But nowadays, many farms, many farm ponds we find as storage ponds actually. So many times the ponds they are fed with water from some other sources like canals or rivers or other sources, maybe from wells. So the provision has been made in this model to have the external inflow from the other sources to the pond. Now, the water demand consists of seepage losses, evaporation losses, and crop water demand, that is for irrigation. So this is the flowchart for the water availability, which is the runoff module, which is based on the curve number method. So this is the flowchart of the runoff model. Then water demand. So water demand consists of seepage. So seepage is given by this equation. So I will not go into the details of the equation. Then evaporation is given by the equation AC T is equal to AT into ET divided by 1000. So ET is the evaporation rate of water from open surface corresponding to the depth of water. Then same thing about the seepage. Then irrigation can be surface irrigation or drip irrigation or sprinkler irrigation. So these are three irrigation methods they have been considered in this model. And there are some irrigation strategies actually. So one strategy is, say, for example, pre-decided irrigation, that is a fixed depth and fixed date. So we give the irrigation on fixed date and fixed depth. Then fixed date, variable depth, that is another strategy. Then fixed date, variable depth. This is based on the climatological approach. The variable depth, variable date. So this is the flowchart of the SWAP 3 model. So this water balance or the farm water balance, farm pond water balance module is attached to the SWAP 3 model, which is again developed by Dr. Gorintiwar. And this SWAP 3 model is a comprehensive model of soil water balance, which gives the continuous soil water balance along with the crop yields and the net benefits. So this is the flowchart of this SWAP 3 model. And this SWAP 3 model is coupled with this farm pond water balance model, and which resulted into the DSS, which is we call is a full DSS pond. Now this DSS is developed in Visual Studio by using the language Microsoft Visual Basic, and the database management system is supported by the Microsoft Access. So these are the results, and these are the screenshot of the model. So this is the input screen of the model. So there are icons like runoff, reference, evapotranspiration, pond characteristics, pond water balance, simulation, and pond optimization. So these are the input details for runoff. So total catchment area. Then a runoff coefficient for the command area, input rainfall data file. So rainfall has to be given with the help of the file. So it can be for number of years. Then you have to select the years. Then this will calculate the runoff from the given data. So runoff will be daily runoff. Then evapotranspiration, there are three methods which are supported by this model: Penman-Monteith, pan evaporation, and Hargrave-Samani. So we can select any of these three methods based on the availability of the data with the user. Then this is the screenshot for Penman-Monteith method. Then this is the screenshot for the reference city for Penman-Monteith constants. This is the screenshot for reference city interface for Hargrave-Samani method. The above is the reference city interface for pan evaporation method. So we have to select the data files. Normally, these are all climate data files, and the model will give the output in the form of daily reference evapotranspiration. Then this is upper is the screenshot of pond characteristics. So you have to provide whether it is a rectangular pond on trapezoidal pond or cylindrical pond, then whether it is full dugout or half dugout. These are the screenshot for interface for full dugout pond and half dugout pond. So you can fill all the details. So length of the pond at surface, width of the pond at surface, total depth of the pond, bottom length, bottom width, top length, top width, total. So it will give total pond volume. It will calculate the total pond volume. Then pond surface area, bottom area, top area. All these areas, it will be calculated, areas and volumes. Same thing about the screenshot for of interface for rectangular half dugout pond. Then these are the screenshot for of interface for trapezoidal full dugout, trapezoidal half dugout pond, then circular full dugout and circular half dugout pond. So the geometrical length, width, depths, slopes, we have to give as input, and then the model will calculate the different areas and the volumes. And these areas and volumes, they will be required for the calculating the water balance components of the farm pond. Now this is from demand side. So for crop water demand, you have to input the crop details in this screen. That is the name of the crop, then code, sowing date, harvesting date, crop period, root zone model. So different root zone models are there. They are provided. You can use the suitable model based on your data. Then KC model and KY model. You have to select all these models. Then this model will calculate the crop your transpiration based on the different inputs given to this crop module. So on the right hand side, these root zone depth and different cases they are given. Then this is the screenshot of interface for editing and adding the different crops. And just like crop information, you have to give the soil information. So type of soil, the soil code, soil layer. So you can consider different layers of the soil. Then soil depth, field capacity, wilting point, then initial moisture content. At the bottom, it is the screenshot of interface to edit and add the soil data into the database. So you can add more soils to this database. Then these are the screenshots of interface for irrigation data input. So you have to give the name of the farm, then crop name, period, soil, initial moisture content, area, then irrigation type and irrigation strategy. Then another is a screenshot of interface for pre-decided irrigation strategy. Then at the bottom, there are screenshots of interface for fixed depth, fixed day irrigation strategy. Then on the right hand side, it is a variable depth irrigation strategy. Then drip irrigation scheduling interface for user specified. So this is the screenshot for drip irrigation. Then on the right hand side, drip irrigation scheduling interface for default. That is the default strategy. Then it is at the bottom, it is drip irrigation scheduling interface for climate specified. So that is based on the climatological approach. Then these are the screenshot of interface for soil water balance. So you get all these parameters, that is runoff, then reference evapotranspiration, KC, then actual evapotranspiration on the daily basis. And at the bottom, you get the actual yield, then total irrigation, total yield, total cost, total benefit, and net benefits. This is the pond water balance optimization screenshot. So you get all the pond water balance parameters in this screenshot. So just I will discuss this model with the help of one small case study. So this is the case study of an area which is 2.33 hectare. Then there are total two numbers with areas 0.85 hectare and 1.48 hectare. Both the catchments, they are row crops. They are contoured. They are very good. They are good hydrological condition, and hydrological soil group is C and D. So the bottom graphs give the rainfall during the year 2015 and 2016. So these are different weather parameters: wind speed, maximum temperature, minimum temperature, maximum relative humidity, minimum relative humidity, sunshine hours. So all these are input to the model. So these are the different parameters for the estimation of PTR by the Penman-Monti method. Latitude, longitude, elevation, height of wind speed, then AS, BS, albedo, constant A and constant B. Then details of the dimensions of trapezoidal flower pond. So in this case, trapezoidal shape has been considered with full dugout type. And depth of the pond is 3 meter, slope is 1:1, top surface length is 25 meter, top surface width is 20 meter, and depth interval is 0.001. So this is the interval which you can select for simulating the level of the water in the pond or the pond water volume. Then these are the different details of the onion crop, that is sowing, harvesting, crop period date, then root growth model, then allowable depletion factor, then crop coefficient, then yield data, then yield response model, main produce to byproduce ratio, then economic information, there is the cost of cultivation, cost of water, cost of application of water, price of main produce, price of byproduce. These are the same details for the sorghum crop. And these are the properties of the soil in the command area of the farm. That is, it is clay type, moisture content at field capacity is 43, wilting point is 17, available soil depth is 2500 mm. Available soil depth 25 mm, 25 centimeter. Details of irrigation strategies considered for onion and sorghum. So these are the irrigation strategies. For onion, it is climate specified. For sorghum, it is pre-decided. And irrigation interval for onion, it is drip. So irrigation interval is alternate day. For sorghum, it is surface, and irrigation interval is 21 days. In case of onion, as it is drip irrigation, application efficiency is considered as 90%. For sorghum, it is considered as 75%. And these are the results. So for subcatchment 1 and subcatchment 2, the model calculated the curve number as 86 and 86. So weighted curve number is 86. Then total runoff depth and volume for the year 2015 and 16, they come to as 21.32 mm and 18 mm for 2015 and 2016. And total volume of water is 496.76 meter cube and 419.4 meter cube. So these are the runoff events during 2015 and 2016. So you can see in 2015, there are just a couple of runoff events, and in 2016, there is only one event which gives inflow to the pond in the form of runoff. Then at the 2015 and 2016. So you can see the crop water requirement or the ETR is throughout the year, whereas we have runoff only during maybe 2 or 3 days during the year. So we have to store this runoff water in the pond and supply the need of the crop water requirement during the remaining period. Of course, this is not possible throughout the year, but it is expected that the pond should support the irrigation during the monsoon and the post-monsoon season. So these are the simulation results for onion and sorghum crop. So for onion, the area is 10,000 square meter. Irrigation type is drip. Then application efficiency 90%. Actual yield is 40 tons. Total yield is 40 tons. Total irrigation depth is 325 mm. Total cost is say 1,677,000. Total benefit is 2,64,000. Net benefit 1,64,000. BC ratio 2.63. Same thing with sorghum. And total irrigation depth is 350 mm. This is the pond water balance for onion with 10% deficit irrigation, 10% deficit drip irrigation, and sorghum with pre-decided irrigation. So such kind of say the analysis we can do if we have the modeling tools in our hand. So we can analyze the scenarios. If 10% deficit irrigation is given, what will be the scene or the result on the resulting crop yields, then saving in water. Or if we have say 25% deficit irrigation, then whether we can increase the crop area, something like this. So this is the pond water balance, which gives the values of total runoff, the total inflow, total water demand, total direct rainfall, total water demand for irrigation, total seepage losses, overflow, evaporation volume, deficit volume, and total remaining available volume in pond at 31st May, and net benefits. So all these figures, they are given for different strategies for sorghum and onion. So the conclusion is that the pond volume uh, 1,461 meter cube is useful for onion over an area of 2,000 square meter area with rupees 32,846 net benefits for Rauri region. According to the pond water balance for pond optimization, it is possible to minimize the deficits for sorghum by change in sowing rate appropriately. So this is a good outcome. Then there is a deficit of certain volume at the end of the crop period for certain combinations. This shows that it is necessary to import the water from other sources to meet out this deficit and obtain the specified net benefits. So it says that only based on the rainfall and resulting runoff, it will not be possible to give the water for certain combinations of crop. So it is necessary to import the water in the pond from other sources, maybe from canal or river or surrounding wells. The study showed that the size of the farm pond depends on the water availability from the catchment area of the farm pond due to rainfall over catchment area, filling and refilling of pond from the external sources, water demand of the crops grown in the command area of farm pond, water balance in farm pond that is influenced by evaporation, seepage, inflow and outflow. In order to decide the appropriate size of the farm pond for the maximum benefits, there is a need to develop the DSS. And so it shows the importance of the DSS to answer all these questions. The decision support system, DSS pond, developed in this study is user-friendly software that allows user to interact with the model input options as per the needs and decide upon the crops to be grown, irrigation scheduling to be adopted for different crops, and the farm pond size, type and shape. As the developed DSS is modular, the DSS pond can be used for the estimation of runoff by soil conservation service method, simulation of crop yield and net benefits, reference crop evapotranspiration estimation separately. The repetitive use of DSS pond for different combinations of farm pond size, shape and type, crop and crop mix, irrigation scheduling strategies lead toward the optimization of farm pond for the given situation of water availability. So this is the beauty of these modeling tools, which gives answers to different say questions. So whether if the cropping pattern is changed instead of the cereals, suppose we have horticultural crop, then what will be the effect on the size of the farm pond? Or if there is a change in the rainfall pattern in the future because of the climate change, how it will affect the size of the farm pond, which we need to take into consideration beforehand. Then if again these kind of studies, they can be replicated in space and time. So for example, if you have experimental data, it is applicable only to that specific location. But if you have the modeling tools, then we can use these results for other locations geographically and also at different time intervals, if you have the data. So this was one model study. Another is based on my PhD research. So this case study is based on my PhD research, and I developed a model for designing the system of tanks in the watershed. And I named this model as soft tank model. And there are some research hypotheses. For example, say in situ rainwater harvesting systems, they influence the storages of downstream ex situ rainwater harvesting system, that is tanks. And hence, both in situ and ex situ rainwater harvesting systems should be considered together in the methodology for optimum design of tank systems in the watershed. Then rational design of tank system for the watershed should be obtained by investigating different scenarios that result from the combination of number of tanks, their locations and types. So, for example, the tank, there are suitable tank locations in the watershed, or suitable sites, you can say. So there may be, say, 5 sites for constructing the tanks. So we can have 5 tanks, or we can have 3 tanks, or we can have 1 tank only. And many times we find that the tanks, the water in the tanks, apart from the recharge, it can be used for irrigation. So the irrigation can be given in the upstream of the tank, or it can be given on the downstream of the tank. So based on all these factors, the hypothesis say that these factors should be considered while designing the tanks in the watershed. Then there is a need for integrating different storage systems. So as you know, the water is stored in the watershed, in the soil, or in the surface tank, or in the aquifer. And all these 3 storages, they are interlinked. So while these 3 storages should be integrated while optimizing the use of available water for crop production, and thus in turn for the optimum design of the tank system. Then another hypothesis is it is possible to design the optimum tank system for the watershed for a desired downstream release of water. Now, when we construct these check dams or percolation tanks on the streams, or say farm ponds on the off of the streams, we don't know how much water we are harvesting. Whether it is say 20% of the inflow, or 50% of the inflow, or 70% of the inflow, we don't have the answer to these questions. But if you have analytical tools in the form of some simulation or optimization models, we can give the answer to this question, whether we can harvest 20% or 50%, or whether we can design the tank systems for pre-decided downstream release. So, hypothesis says that it is possible. The variability in supply and demand parameters influences the optimal design of the tank system. So, if there is change in the climate and resulting rainfall and runoff, it will affect the supply and it will affect the tank system design. Same thing when there is change in the climate, there is change in the crop transpiration requirement. So there is change in the demand. So all these supply and demand parameters, they will affect the tank system design. So based on this hypothesis, this research was carried out, and it is conceived that this in watershed, all these in situ and ex situ rainwater harvesting practices, they are integrated. So this is the conceptual figure of integration of 3 storage systems in the watershed. So that is the tank storage on the stream, or maybe off the stream. Then soil storage, which is a thin layer of ground, maybe from say as less as 7.5 centimeter to as high as say more than 90 centimeters. Then there is aquifer storage in the form of groundwater. So these storages, they store the water which is from rainfall, runoff, and again which is used for the domestic purpose and agriculture purpose. So I reviewed the literature of these modeling approaches and found that there are studies for single tank systems and multi-tank systems. And the studies approaches were empirical, then simulation modeling, then simulation optimization modeling, and mathematical modeling. And then I found that there was some scope for simulation optimization modeling for multi-tank systems in the watershed. So this is a flowchart of the soft tank model. Of course, this is a conceptual flowchart. The detailed flowcharts I have not given. So first, the possible locations of the tanks, they are identified on the streams. That is the main stream. Then fields, they are allocated to these possible locations. Then the tank strategies, they are generated based on the tank location and the tank types. Then the catchment and command fields, they are allocated to these tanks. Then different tank strategies, they are generated, and the simulation is started from tank strategy number 1. Then tank dimensions, they are calculated. Then daily simulation of field, tank, and groundwater balance is done. Then the DSR, that is downstream release from the watershed, is computed. And if the downstream release is within the range of system downstream release, the simulation is stopped. If it is not, then it is repeated. And then project economics and strategy details, they are calculated. So this is a conceptual flowchart. This model can be run in 4 modes, that is calibration mode, evaluation mode, simulation mode, and optimization mode. So in calibration mode, the model takes into account the groundwater levels for calibration. So this is the example of the calibration of the model for one Pimpalgaon is the watershed near Ahmednagar in Maharashtra. So the blue lines, inverted blue lines, they are the rainfall. And the following 2 lines, the lines with the circles, they are the computed groundwater levels, and the straight curved line is the observed groundwater level. So the computed groundwater levels, they are underestimated by the model, but the trend is quite close to the observed groundwater levels. Then again for evaluation modes, the example of the same watershed is given. So this is Pimpalgaon Ujni watershed. There are 2 tanks, big tanks on the streams. So these are second order streams. There are of course wells and agricultural fields are there below the tanks. Then this is the contour map. This is the hydrological soil groups. So the watershed area, it comes under the hydrological soil group B, C, and D. These are the land use of the watershed. So you can find that most of these agricultural crops, they are just in the command area of the tanks. In the catchment area of the tanks, there was no cropping practiced. So there are kharif crops, then there are rabi crops, there are double crops, there is a fallow land, and there are shrubs. All these practices, they are marked in this land use map. So after running the model in this evaluation mode, we found the field water balance components. So you can say from 1975-76 to 2003-04, all these field water balance components, they are shown in this figure. That is the rainfall, then irrigation, then runoff, then evapotranspiration, and deep percolation. Now, how these field water balance components, they are used in deriving the conclusions, that will I will just discuss later. So field water balance components, annual rainfall was 541 millimeter, then runoff was 21.5% of the rainfall. Then evapotranspiration was 67.5% of the total outflow. Deep percolation was 15.8% of the total outflow and 20.5% of the rainfall. Now this is the individual tank water balance. So the tank capacities for tank number 1 and tank number 2. So tank number 1 was on the left hand side and tank number 2 was on the right hand side on the stream. So tank capacity of tank number 1 69.59 hectare, for tank number 2 21.69 hectare. Inflow in tank number 1 was 42 hectare meter. For tank number 2 it was 32.69 hectare meter. Overflow for tank number 1 was 0. For tank number 2 was 3.38 hectare meter. Evaporation from tank number 1 was 6.03 hectare meter. From tank number 2 it was 4.20 hectare meter. Seepage 36.23 hectare meter and 25 hectare meter from tank number 2. So these are individual tank water balance components. Then groundwater recharge and withdrawal components. So the model says that the recharge from the tank was 29% in the watershed and recharge from the field was 71%. And whereas the irrigation water use was 66% of the total use and best flow was 33% and other use was 1%. So this is the summary of the evaluation study. So annual rainfall in the watershed is 541 millimeter. Total area is 1,326. Number of tanks in the watershed 2. Purpose of these tanks was groundwater recharge. Runoff in the watershed as a percentage of the rainfall was 21.5. Field recharge to groundwater as percentage of rainfall was 20.5. Then inflow tank capacity ratio was 0.82. So it means that the tank, they are not filled to their capacity as the inflow tank capacity ratio was less than 1. Then downstream release was 58.5%. So it says that this tank system over a period of say 20-25 years for which the data was used, the 58.5% of the inflow was harvested by these tanks and only say 42% was going as the outflow to the downstream side. Then tank seepage as percentage of the inflow was 83.6%. Evaporation from the tank was 13.6%. Then tank irrigation 0 because they were especially for recharge purpose, percolation tanks. Then field recharge as percentage of total recharge was 71%. Tank recharge as percentage of total recharge was 29%. Groundwater flow 33%. Groundwater irrigation 65%. Other use 1%. And the BC ratio of this system was 1.34. So conclusions from the evaluation study: 42% runoff is harvested by the tanks and 52% of the runoff goes as downstream release from the watershed. Inflow tank capacity ratio, which is 0.82, suggests that tanks are not filled to their full capacity and hence they are over-designed. If any in-situ rainwater harvesting treatments like CCTs are taken in the catchment of the tanks, they will further reduce the inflow to the tanks, and hence it is not recommended to carry out any in-situ rainwater harvesting practices in this watershed. Now, the same model can be run in simulation mode, and in simulation mode, say for example, there are three strategies we can test. The tank strategy number 49, which gives two tanks at location number say 2 and 4, shown in the figure on the left hand side. Then tank strategy number 58, where tanks are at location number 2 and 5, and tank strategy number 94, where the tanks are at location number 3 and 6. So these different strategies we can test how it will result in the total benefits of the system, what will be the crop yields, what will be the water balance components. So in simulation mode, you can see for the different strategies, we have irrigated area, we have irrigation volume, we have runoff, we have deep percolation. So I will not discuss all details, but just go to the conclusions. Then simulation mode, in simulation mode, the model has given these tank capacities for tank number 1, tank number 2, for these different strategies. What will be the total storage capacity of the tanks? What will be the inflow capacity ratio of tank 1 and tank 2? Then groundwater balance components. What is the total? What is the field recharge? What is the tank recharge component? What is the irrigation component? What is the other use? What is the best flow? So in this case, we have assumed that tanks are also used for irrigation. So that's why this irrigation volume has come. Then project economics. So for these different strategies, these BC ratios they are given, then benefits are given. So we can see that tank strategy number 49, which is the strategy. What is the meaning of 49? That I will tell you. But this tank is used for groundwater recharge, and for irrigation, both. So strategy number 49, I will just show you. So this is tank strategy number 49. So we should locate the tank at this location number 2 on the left hand side, location number 4 on the right hand side, and the irrigation, the water can be used from the tank on the upstream and downstream side for irrigation and also for groundwater recharge. This is how we can use this model in simulation mode for simulating different strategies. We can have different cropping patterns. We can simulate the effect of different cropping patterns on the tank system design. We can simulate the effect of different climate scenarios on the tank system design, different soil types. And now the optimization mode. So in optimization mode, the system is run for different years for all the strategies and for different downstream releases, say from 20 to 90 downstream release. So 20 downstream release means we are harvesting 80% of the rainfall runoff in the watershed, and 20% we are allowing to go downstream. DSR 90%, it means we are just harvesting 10% of the runoff and rainfall, and 90% runoff is going downstream of the watershed. So like this, for different downstream releases and for different years, we get one optimum tank strategies by simulating all the tank strategies. So tank strategies may be in few thousands based on the number of possible locations. As the possible locations goes on increasing, the tank strategy number goes on increasing exponentially. So for example, during the year 75-76, for 20% downstream release, the model has given 1,804. This is the number, this is the ID, you can say, not the number, tank strategy ID, which represents a particular number of tanks, the locations in the watershed. Then for 30% downstream release, the tank strategy number is 49. For 40% downstream release, tank strategy number is 85. For 50% DSR, tank strategy number is 913. For 60%, it is 994. For 70%, it is 373. For 80%, it is 58. For 90%, it is 60. So this is based on economics, BC ratio. So it says that these strategies, they are the most economical for these downstream releases for this particular year. So like this, we get different tank strategies. Then again, for this different input DSR, we also get output DSR, because this output and input DSR normally they don't match. They divide within 10%. So these are the tank strategies. This is the initial cost. Then this is the maintenance cost. Then crop cultivation cost, total cost, gross benefits, net benefits. These are the BC ratios. So like this, we get these cost economics of different tank strategies for different downstream release. Then we can plot this graph of downstream release versus net benefits. Then we see that as the downstream release goes on increasing, say up to 50%, the net benefits of the system goes on increasing. Then further increase in the downstream release does not increase in the net benefits. Then we say that this is the tanks system which use downstream release about 50%. That is the most beneficial, and then we recommend that particular tank strategy for that watershed. So this is the say in this Pimpalgaon Ujni watershed, this is the tank strategy number 94, which is existing. That is, there are two tanks. One tank is on the left-hand side at location number 3, and one tank on the right-hand side stream at location number 6. And the tank strategy which the model has given, that is optimum strategy, that is the tank strategy number 85, which says that the left-hand side tank is at location number 3. That is the same location which was in the existing system. However, on the right-hand side, the model has suggested the tank at location number 5, which is just downstream of the location number 6. So if say on the other hand, if we say that if this model we would have used while developing the Pimpalgaon Ujni watershed, maybe this would have been our recommendation for that watershed. That instead of constructing the tanks at this point number 3 and point number 6, we should construct the tanks at point number 3 and point number 5. And these are the tank dimensions of the optimum tank strategy. So for tank number 1, capacity is 36 hectare-meter. For tank number 2, capacity is 56 hectare-meter. These are the different dimensions, and these are the existing capacity and simulated capacity of the tanks. So for existing capacity for tank number 1, 36 hectare-meter, and the simulated is 69 hectare-meter. For tank number 2, it is 56 hectare-meter existing, and simulated is 21 hectare-meter. So there is quite deviation in the tank capacities. Then we can have modeling studies for in situ rainwater harvesting. So I will just discuss a couple of studies. This is again based on research of PhD research of my student. We have done the simulation modeling of these ridges and furrows. So the research was simulation modeling of ridges and furrow system for assessment of water harvesting potential in a semi-arid region. And these are the objectives: to develop the methodology for simulating different components of field water balance for in situ rainwater harvesting, that is ridges and furrows. To develop simulation model for in situ rainwater harvesting, to measure different water balance components by conducting field experiments, calibrate and validate the model, and to Maharashtra based on simulation runs of the model using the historical climatic series. So we found, we studied the literature, found research gaps, and therefore conceived this hypothesis and finalized the objective. So this is the conceptual sketch of Regis-and Furrow rainwater balance. So there is inflow to this Regis-and Furrow in the form of rainfall. And though it is assumed as rain-fed, but still we have provided, or we have made the provision of protective irrigation. So if protective irrigation is given, then irrigation is another source of inflow. Then outflow from the furrow, there are evapotranspiration, the runoff flow to the soil moisture storage in the root zone. And outflow from the soil moisture storage goes as deep percolation. So different processes involved in this furrow water balance, that is furrow rainwater balance, which is say infiltration through furrow is the difference of precipitation or rainfall minus runoff. Then reference crop evapotranspiration is calculated by Penman-Monteith method. So all these I have also discussed in the earlier modeling studies. Then actual evapotranspiration, soil water depletion factor, root growth function. So this furrow rainwater balance is again coupled or not coupled actually, but the output of the furrow rainwater balance is given to the swap creep model described earlier in the Parpon water balance model. So this is soil water balance equation. Then output from the soil water balance equation goes as the deep percolation. This is the crop growth model. Then estimation of net benefits. Then statistical analysis. Then analysis of data for computation of CN ratios. Then development of actual simulation model for Regis-and Furrows. These are the assumptions in the model. This is the flow chart for curve number. Then this is furrow rainwater balance model flow chart. These are field experiments. Field experiments were conducted during the year 2015 and 16. So 4 treatments were taken with 30 centimeter Regis-and Furrow, 60 centimeter Regis-and Furrow, 90 centimeter Regis-and Furrow, and control, that is without Regis-and Furrow. So this is the layout, field layout of the experiment. So T1 means 30 centimeter Regis-and Furrow, T2 means 60 centimeter, T3 means 90 centimeter, and T4 is control. So these runoff plots, they are available on the research field of the Department of Soil and Water Conservation Engineering. And there are 2 plots. So the same is replicated on another plot. There is stilling basin and multi-slot divisor is there. So 1/10 of the runoff is collected in the collection tank on the downstream side. The excess runoff goes to the main drain. The individual treatment plot size is 12 meter by 28 meter. And the total plot was of the size of 48 meter by 28 meter. Then physico-chemical properties of the experimental soil were determined. Then all cultural operations standard practices were followed. Soybean crop was manually developed at the spacing of 30 by 10 centimeter. Daily weather data was collected. Soil moisture content was taken at 15, 30, 45, and 60 centimeter depth at the upslope side, middle of the plot, and at the downslope side of the plot. Then runoff was measured. Curve number was estimated for different dimensions of Regis-and Furrows. So this is how the runoff calculations were done. Then curve numbers were estimated based with the help of the rainfall and the measured runoff from different Regis-and Furrow. Physical properties of the soil. So the textural class of the soil is clay loam. Field capacity is 29%. Permanent wilting point is 14%. Bulk density 1.3. Basic infiltration rate 19.3. These are the chemical properties. Then cultivation details of the crop for the year 2015 and 2016. So the crop was sown in in the month of July in 2015 and in the month of June in 2016. And it was harvested in the month of October. Total crop duration was 102 and 114 days in 2015 and 16 respectively. And total rainfall during crop growth period in 2015 it was 210 mm, whereas in 2016 it was 629 mm. So you can say these are all the both years were extreme. So 2015 was drought year, whereas 2016 was wet year. So ridges and furrow rainwater balance components, they were measured. That is rainfall, runoff, infiltration, soil moisture for both the years. So these are the components. These are the runoff for 2015. These are the runoff figures for 2016. Though we could not take many events of runoff because it was all flooded. There was no access to the field, and all this multi-slot divisor was overflowed, and we had to skip some runoff events. So total runoff, total rainfall during 2015 was 1 mm. Because we did not consider the extreme events. That's why this is 182. Actually, though the rainfall is 629 mm during 2016, we have to skip many observations because of the flood situation. Then this is how the curve numbers were estimated. So we estimated the curve numbers for different dimensions of the ridges furrows. These are the main observed curve numbers for 30 centimeter, 60 centimeter. For 30 centimeter ridges and furrow, 79.77. For 60 centimeter, 72. For 90 centimeter ridges and furrow, 68. And for control, it was 81. Then these curve numbers were validated for the data from the year 2016. Then these are the infiltration values. Then these are the soil moisture values during the crop growth period for 2015. This is for 2016. Then observed crop yield and benefits during 2015 and 2016. So we can see these BC ratios for different dimensions of ridges and furrow during 2015 and 16. Now, this is the layout of the ridges and furrow. So the topmost is 30 centimeter, the middle one is 60 centimeter, and the bottom is the 90 centimeter. We did not change the plant spacing actually, and the same ridges and furrows were different. And it affected the location of the plant. So in the 30 centimeter, the plants took the position at the top of the ridge. Then in the 60 centimeter ridges and furrow, the plants got located on the mid of the sloping position of the ridge. And in the 90 centimeter ridges and furrow, the plants got located at the top and at the mid of the sloping position on both sides of the ridge. And different ridges, they have got different depths, different top widths, different surface area, which again affect the hydrology of the ridges and furrows. So this is the simulated and observed soil water moistures, soil moistures. '60, '90, and control. Then we found that at lower depths, there are not much difference in the soil moisture among different dimensions of ridges and furrows. But for 15 centimeter, top 15 centimeter, there was variation in the soil moisture. And the 90 centimeter ridges and furrow, it had less soil moisture as compared to 60 centimeter and 30 centimeter ridges and furrows. Then this model was applied to the climatic series of 20 years of climatic data for Rauri, and furrow rainwater balance and crop yields were simulated. So this is furrow water balance calculations. Then these are the simulated yields. Then variation in the soil moisture in the root zone in 2015 and 16. This is for 50, for 30 centimeter, 60 centimeter, 90 centimeter ridges and furrows and control plot. This is for the year 2016. The years were also classified in different type of years, like dry year, normal year, and wet years. for better analysis of the hydrology based on the nature of the rainfall. So this is the rainwater balance components scenario for dry years. So these red bar graphs, they are infiltration, and the blue are the runoff, and the green are the deep percolation. So above graph is for dry years, that is, and the below graph is for wet years, and the crops, they are rain-fed. So again, the water balance, Regis and Furrow water balance components for normal years and for all years. Now same is repeated for irrigated scenario. So in rain-fed scenario, we have not simulated the irrigation. It is totally rain-fed crop. Whereas in irrigated, we have simulated the protective irrigation. So normally in our irrigation studies, we give the irrigation at 50% soil moisture depletion. But in this case, we have increased that ratio up to 60%. So when 60% of the available soil moisture is depleted, then the protective irrigation should be given. The purpose is to have the crop solely on the rainfall or the rain-fed, and as far as possible postpone the irrigation. So irrigation is given just for survival. So these are the Regis and Furrow rainwater balance components for the irrigated scenario. So this is a comparison of these hydrology components for dry years, wet years, then for normal years, and for all the years. Again, simulation of soil moisture in the root zone for 2015-2016. This is the simulation of the crop yields. So you can see for wet years, the crop yields are maximum. For dry years, the crop yields are minimum. So dry years, they are denoted by these blue bar graphs, and wet years, they are denoted by the red bar graphs. And the percentage of yield reduction for rain-fed scenario. So as compared to the irrigated scenario, there is a huge reduction in the yield because of the rain-fed scenario. So for T1, this is for T2, this is for T3, this is for T4. Then simulated yields based on the seasonal rainfall and number of irrigations required. So this we did something extra kind of thing, that is the dry, wet, and normal years which are defined by the IMD. They are based on the annual rainfall values. But actually, the distribution of the rainfall matters more as far as the irrigation is concerned. So we simulated the irrigation scenes, and based on the irrigations required, we again classified the years into dry, wet, and normal. And we found those results more encouraging actually. These are the runoff plots in which the experiment was taken. This is the crop scene in 2015. So this is the conclusion. The methodology has been developed for simulating region for rainwater balance components. It has been converted into Excel programming by simulating water balance components. Different water balance components of Regis and Furrow system were measured by conducting the field experiment. Then model was calibrated and validated. In the field, the CN ratios were developed for different Regis and Furrow. So we don't, earlier we didn't have CN ratios for different dimensions of the Regis and Furrow. So in this experiment, we developed this CN ratio. Now, based on the simulation results of 22 years, we recommend that construction of 60 centimeter Regis and Furrows is the best or the optimum for better rainwater harvesting and better yield of soybean in the semi-arid region. So out of 30 centimeter, out of 60 centimeter and 90 centimeter Regis and Furrow, we found that 60 centimeter is the best size of the Regis and Furrow for such type of climate, a semi-arid climate like Rauri, or taking the yield of soybean during the Kharif season as a rain-fed crop. So it is almost end of the time. I will just take 5 minutes. Again, to illustrate the importance of the modeling study for another in situ rainwater harvesting practice. So this was again part of my PhD. So we assessed the groundwater recharge through CCTs by simulating the CCTs in the model. So this is the conceptual sketch of the continuous contour trenches. So there is a trench on the upslope side. There is a bund or the soil which is excavated from the trench is put in the form of bund on the downslope side. Many times the plants are grown on these bunds and from runoff, and outflow from the trench is normally the inflow to the groundwater table. This is the actually photo of the CCTs, continuous control trenches on the field. So these are the objectives to derive the simulation model for assessment of groundwater recharge through CCTs, to estimate the water intercepted by the CCTs, to estimate the groundwater recharge through CCTs. So this is the flow chart of the simulation model of the CCTs. These are the assumptions. Each model is based on some assumptions. So for example, rainfall is uniform over the entire trench field. Cross section and the water depth in the trench, they are uniform. Congestion is considered as minimum and hence it does not influence the infiltration in the trench. Groundwater table does not interfere with the infiltration process. Inflow into and outflow from the trench, they are instantaneous. So these water harvesting potential of the trench system was defined something like this: gross and net water harvesting potential. So inflow to the trench minus outflow from the trench divided by inflow was considered as gross water harvesting potential, and inflow minus outflow plus evaporation from the trench divided by inflow to the trench was considered as net water harvesting potential. So that means net water harvesting potential gives the groundwater recharge as a shows the groundwater recharge. So that is the difference between the gross and net water harvesting potential. So this is the definition sketch of the trench system. There is runoff to the trench, there is overflow from the trench, evaporation from the trench, then infiltration to the soil zone, which again goes further to the water zone and the groundwater table. So different process representation. Runoff was calculated with the SSCN method, infiltration by Green-Amt equation, evaporation by Penman. This is the case study of the small watershed from Akola, 7.5 hectare. CCTs at 5 meter horizontal interval, land use is vertical. So this is not to the scale sketch of this micro watershed. There are 2 fields with CCTs, and there are 2 tanks at the end of this micro watersheds. So climatic data is from 76 to 2003-4, 28 years. Then different trench sizes they were simulated. For example, 0.3 by 0.3 meter cross section, 0.6 by 0.3 meter cross section, then 0.6 by 0.6 meter cross section. This is the existing size, 0.6 by 0.3 meter. And one was taken as half of the existing size, and one was taken as the twice of the existing size. Then different spacing were simulated. That is 5 meter, which is the existing spacing, then 10 meter and 20 meter of the existing, 2 times and 4 times of the existing spacing. Soils of the micro watershed properties were given, and this is what we got after the as a result of the simulation. So different rainfall, year-wise rainfall is given, number of rainy days, then the runoff, then again number of runoff days, then gross water harvesting potential, which is 100%, and net water harvesting potential, which is groundwater, which has will be the groundwater recharge component. It varies from 89% to 67% during the different years. And these yellow figures, years with yellow figures, the data was taken for further study. So these are the water balance components of the trench system. The top one is the evaporation, then the below is infiltration, then that is the runoff, and the dark one is the inflow to the trench system. And we can see the 1988 year with very heavy rainfall has stands tall in these different graphs. So this is the water harvesting potential as a function of trench spacing and size. So you can see that for P1, P2, and P3, P1 is the closer trenches, P2 is further away, and P3 is further away. So water harvesting potential decreases as the trench spacing increases. And again, water harvesting potential increases for bigger size of the trenches. And this is the graph which shows water harvesting potential as a function of the investment cost of the trench system. So this is quite useful in the project planning stage. So based on the money available with us, we can go for the size of the trenches and the spacing of the trenches, because it gives the water harvesting potential as a function of the total investment cost. So this groundwater recharge through the trench system, these 4 years they were considered. So groundwater recharge, this is the observed and this is the computed. The computed groundwater recharge, they are underestimated than the actual observed groundwater recharge, but still the trend is the same as the observed one. So the conclusion is, this gives the simulation model for a water balance of the trench system. It is possible to understand the effect of the governing parameters like rainfall and trench geometry on performance of the CCTs with the help of the model. Though model under-predicted groundwater levels, but they do not deviate greatly, and model can be used for assessing groundwater recharge through CCTs. Average contribution to groundwater recharge through the trench and the field are 53% and 47% respectively. So this is all from my side. So the message is that for rainwater harvesting interventions for climate smart agriculture, we should have such modeling studies, and these modeling studies should be coupled with the data which shows the change in the climate, the GCM and RCM models, or it can be derived locally by the trend analysis of the historical data. So if you take into account these data and input to such kind of models, you can have the rainwater harvesting, which will be, we can consider as rainwater harvesting for climate smart model. That is the message from this lecture. And the engineers or the staff and the students who are in their beginning of the career or mid of the career, they can go for, because there is a lot of scope. There are many practices which are still to be modeled, and you can go for modeling of these practices and use these generated data series for making these rainwater harvesting practices as climate smart watershed practices. Thank you.
Yes, thank you very much, sir, for a very informative lecture and presenting some important modeling tools like Fully DSS, Swap Creep, and Soft Tank model. Also for presenting some experimental case studies regarding rainwater harvesting. So there are a few questions in the chat box. Shall I take one by one?
Yes, you can take.
Yes, sir. There is one question from Ms. Pranali Naitham. Sir, does these models are available publicly?
These models, they are not available publicly because they are not user-friendly model. That is the main problem. But we will try to make it user-friendly, and then it can be shared in the public domain.
Okay. Thank you, sir. Next is Dr. Gaurav Singh. How the recharge from tanks and field was individually measured or estimated, and how was the seepage measured?
Seepage, actually seepage was not measured actually. Seepage was the last component. So it was estimated indirectly, you can say, from the water balance.
Okay. Next question is from Nivedita Dubey, ma'am. What is the criteria of defining dry or wet years?
So that is given by the IMD. If the rainfall is less than the 50% of the average annual normal rainfall, then it is dry year. If it is more than 1.5 times of the normal year and for it is wet year, like this. There are 2-3 criteria actually. They also vary. So we can have any one of those criteria.
Next question is from Dr. Siddharam Patil, sir. What kind of simulation model you would suggest in public water management? Does this simulation model will help to overcome from the water crisis?
What kind of simulation model?
You would like to suggest in public water management?
What you mean by public water management? So what I discuss, there are also public water management, you can say. Does he mean that public water distribution system for domestic, something like that?
Dr. Maunskar, you can unmute the person who has asked the question and let's have the conversation with the expert directly.
Yes, sir. Patil, sir, you can ask your question. You are unmuted, sir.
Actually, sir, that one public water management means that public water distribution system, sir. In general, will follow in rural areas. Water distribution system.
Yeah, that is that is a different thing actually, which I didn't discuss actually, and I have not studied also. That is simulation modeling of water distribution system through pipeline. But I think, can I request Dr. Gorantiwar to say something on this? He has worked on this kind of study.
Okay, sir.
Just a minute.
He is asking about the simulation modeling in a piped water distribution system.
Yes, there is one software available which is in free domain, and that is EPANET actually.
One, sir.
EPANET, EPANET.
Okay, sir. Okay, sir.
Environmental Program Agency, and this is quite versatile software, very user friendly. And in fact, we are trying to get some experts on EPANET and to have one training on that, but yet we didn't get, but we'll try. But I think you being engineer, you yourself can work on that, okay? And you can refer to that software, and which is very good for the piped distribution network of any kind.
Okay, thank you very much, sir. Next question is from Shashikant Maitre, sir. Can we quantify groundwater recharge due to various surface and subsurface interventions in the watershed on the basis of runoff or cropping pattern, decision to overcome supply and demand gap?
Can you, Vaibhav, can you repeat the question again?
Can we quantify groundwater recharge due to various surface and subsurface interventions of watershed on the basis of runoff for cropping pattern, decision to overcome supply and demand gap?
Yes, we can very well differentiate these things through this the tools which I discussed, Maitre. So I think we can continue the dialogue, Shashikant, after the lecture also. So you can contact me. We'll discuss the further things.
Okay. Okay, these are all about the question answer, sir. Thank you very much. Now I would like to invite one of the participants, Engineer Vidya Kandekar, to propose vote of thanks. Vidya ma'am, please.
Yes, very good morning to all. It's my great privilege to propose a vote of thanks for today's session. On behalf of all the participants, I would like to thank Dr. M.G. Shinde sir, Professor SWC and Co-PI, CAST CSAWM Ravri for your informative session on rainwater harvesting for climate smart watershed. And also thank you, sir, for sharing your research studies with us, which can definitely help us to understand how rainwater harvesting is useful and how we can go for the rainwater harvesting. Also, I would like to thank all the whole organizing team for organizing such wonderful session. And also, I would like to thank all the participants for their valuable time. Thank you, sir.
Thank you, Vidya. Shashikant, can you hear me?
Yes, sir. Yes, sir.
Yeah, how are you doing? You can unmute.
Hello. Hello.
Where are you and what you are doing actually?
Yes, sir. I was already unmute, sir.
Where are you nowadays? What are you doing?
Yes, I am now in Nashik base, but working in East India, especially in Bayer for NRM sector, Natural Resource Management, Watershed Development projects, and also other livelihood option watershed development projects.
Okay, seeing you after a long time.
Yes, yes, yes. Yes, sir. That's why thanks for Akbar sir and Gaurav sir also, because this is a very short time. Yesterday night I have joined for registration, and morning I requested to you for specially to join this seminar. There's a purpose, but I want to interaction with Akbar sir, you and Gaurav sir. That's
Okay.
the main purpose.
Okay, okay. Thank you. Welcome to this training.
Thank you, sir. Thank you.
Yes. Doctor?
Yes, sir. Thank you. There is one announcement. In the afternoon at 4 p.m., we will having a second session on watershed management and climate change by Dr. Akhilesh Kumar sir. So all should be ready by 3:30. The link and password will be provided in the WhatsApp group. So thank you all the participants for their patient listening to this today's session. With the permission of today's speaker and our organizing secretary, I declare this session is over. Sir, shall I end the meeting?
Yes, yes, definitely. No problem.
Okay, thank you one and all.